So, Simon and Ron, welcome to my mad science laboratory here.
Laboratory, thank you.
So, we are going to talk about science mysteries. These are things that you might think science currently understands, but actually we have no clue.
Oh, I thought these were mysteries for us. These are mysteries
No, this
for
is
science.
mysteries for science in general, okay? So really, if you figure out any of these, you'll probably get a Nobel Prize.
What is light?
Yeah, you'd think we'd know what light is,
Yeah.
but no, not really.
Electromagnetic, whatever.
So, first we'll start with what is gravity, right?
Makes things.
Simon, you know what gravity does?
Yeah,
What does it do?
it makes things stick to the floor.
Yeah, exactly. It makes things stick to the floor, which is unusual because if you were in the middle of space, well, nothing would stick to the floor. Everything would just be floating around loose. But here on the Earth, when I let go of something, it not only drops to the floor, it accelerates. It starts to
Accelerates.
it goes faster.
It goes faster.
Right? Which is weird because the only way that could happen is if, say, we put a rocket on this, and then that would also cause it to accelerate down, right?
But gravity does.
But gravity does that. There's no rocket, and you'd think that it's going to take energy to accelerate that. So that's a big mystery about, and really we still don't have any super good ideas about how that works.
Einstein figured that all out, I'm sure.
Well,
100 years ago.
Einstein, he came up with, I would say, a description of gravity, just like Newton described gravity. He came up with a little bit more sophisticated
What you just said is
set of equations, which were a little bit more precise
not really
than
understanding.
Newtonian, but it like, for example, what Einstein people would say is that gravity is like if you take a big rubber sheet, and maybe you've seen this demonstration, and then they make this big funnel thing, and so it's orbiting around because of that big old funnel thing, and it has to do with space-time. Of course, the funny thing about that is that it's a horrible analogy because that only works because of gravity, right? If I took that rubber sheet and I stuck it up in the space shuttle, I rolled the ball, and guess what? It doesn't work, right?
Mm-hmm.
So they're trying to explain gravity in terms of gravity, which is a gigantic cheat, right? And mathematically, the math is right. The experiments, we're like predicting, say, the orbits of Mercury, which was a big deal, are right. But I would say that it's just not really a satisfying intuition as to what's going on. Now, other people, like, here's some weird ideas for what gravity is. So some people think that there is something raining down upon our head. We're in Seattle here, we always get rained upon. But suppose that it was like rocks and stuff, okay? And that constant things raining down on us, that's what's pushing us down, right? That this is constant rain of something coming down. See, that could be something.
I thought it was an attraction.
Yes, no, it's not attraction. It's like a total push, or another strange. Well, if you ask the mainstream scientists, they would say, well, there's something called a graviton, and between this atom and that atom, they're sending particles at each other, and somehow that causes an attraction, right? They think this might be a particle, but no one's ever been able to find a graviton or anything like it. And here, I'll do one that's really strange, but how, like when you're in a car and you accelerate and you get pushed back against the car, right? That's because when you accelerate, you get pushed back. So the idea is that the Earth isn't actually a fixed ball. what's doing is it's constantly getting bigger at an accelerating rate. So this is like the exploding Earth paradigm where the floor is actually not still. It's actually accelerating upward at 9.8 meters per second.
But then the Earth got bigger.
And the Earth is getting constantly, everything,
But
the
who
universe is constantly getting bigger. And so us standing, I mean, this is like the equivalence principle where, like, you know, Einstein said that if you're in an elevator and you're accelerating upwards, you know, that cannot be distinguished from gravity. That's one thing Einstein would say. And this is just kind of that taken to the absurd level, which is that we're all in just the accelerating elevator and the Earth is constantly getting bigger at a rate of 9.8 meters per second. So that, you know, when I drop this, actually what's happening is that this is staying still. What's happening is that the table is rushing up. The table's rushing up to meet it.
So,
What about, you know,
Seems
that seems just, all those just seem like kind of weird ideas, don't they?
yeah.
Okay, so I have my own ideas, okay?
oh,
My ideas generally rejected, but I'm going to try and convince you
okay.
that what I'm saying is correct.
And if you can convince others.
And what do I say? What is gravity? Well, I'm saying it's the same thing as the electrostatic force. So you may be familiar with that electrostatic force. We know that's just like attraction of opposites, right? So you have positive charged things, you have negatively charged things, and those attract each other, right?
Of course,
See?
those are magnets. It's magnetism, not charge. They're Velcro, so they're not.
Yeah, this is it. But this is only for illustrative purposes. So that's what we generally think of the electric force. We have positive charged things,
Positive and
negatively charged things, and that's what causes the attraction.
And the positive and
Right.
negative come
Right? Positive and negative come
Yeah.
to attraction. But then, you know, how could that be gravity, right? Because people will say, oh, well, gravity is only attractive, right?
Yeah.
Versus
Yeah.
electric fields, which come in positive and
Yeah.
negative. And
Yeah.
gravity only comes in one way.
Yeah. Yeah.
So what people don't realize is that there's a different kind of electrostatic. Everybody knows that opposites repel, right? Opposites repel.
No,
whether it's
likes repel.
well, yeah. Oh, that's right. Likes repel, and opposites attract.
Yeah.
But what people don't realize is that there's another force of electrostatics, which is that if you have like this negative charge hanging out here,
Mm-hmm.
and you have a neutral particle, which is both positive and negative, right?
Mm-hmm.
That's neutral. That this neutral particle will be attracted to this negative particle. Did you know that?
It depends on which way it's turned.
Well, yes, it does. Because what will happen is that because the positive is attracted to negative, it'll turn this way.
Yeah.
And what happens is that this positive is just a little bit closer than that negative.
Oh.
And so that makes the attraction stronger than the repulsion.
Mm-hmm.
So it comes together. And so this means that any strong source of charge is going to attract everything, right? And so, you know,
It's got a turn.
I can kind of demonstrate this. So I don't know if you've noticed back here, but
No.
back over here we've got a few weird things going on here.
The magician has made sure we don't notice back there. He's
You know,
distracted us.
there's like a
He's
straw
distracted us.
stuck to the wall,
Okay.
and now there's a balloon stuck to the wall, right? And there's no glue,
Mm-hmm.
right? All I did was that I added some more electricity onto this balloon, and suddenly it sucked onto the wall.
Yeah, we call it static electricity.
Yes,
We
we
don't-
call
we
it
don't-
static
But
electricity.
we don't understand what, I have no idea what it is.
But the thing is that what I'm going to claim, which would be the controversial part, is that what you're seeing here is actually anti-gravitational. That the exact same force that's causing this balloon to stick to this wall is exactly the same force that's causing your feet stick to the floor.
Oh.
See, and that's it. That's the easy answer. What's gravity? Is it distortion of space-time? No. It's an electrostatic attraction. That's it. So what happens is that the Earth, sitting in space, being hit by the sun, you know, it gets charged up because the electrons tend to get blown off, right? Electrons are very loose. And so that would leave, you know, things like the Earth generally positively charged. Not by much, but added up over the entire volume of the Earth actually becomes quite a strong electric field. And, you know, we witness the strength of that electric field in, like, the weather, right? Like, where do you think lightning comes from?
Lightning?
Yes, did lightning come from there? You know, mainstream, we know there's a, you know, at least a 300,000 volt difference between the ground and space. And it's like, well, where does that come from?
Okay, Simon would like to see a little action here.
Let's see some action.
Action.
This is action. We've got the balloon stuck on, the wall. So, you know, I'm saying that this balloon here is going to be very much like the Earth, right? So, and down here, I have some people and stuff here. See, and what we can do is that we can get those people. Does any of my people stick on there? Yes. We have to wait for this to calm down a little bit. But you see, we got like there's like people and cars stuck onto the balloon here. Now it'll just stay there. You see. And if you were like an ant or whatever on the balloon, you tried to jump up, you would fall down.
Oh, I see.
You would, you know, if
But that's static electricity. That's not gravity.
No, see that's what I'm saying. Static electricity is same. Actually, it causes gravity. I'm saying that's why I'm saying that what you're witnessing here is not a different kind of force. What you're witnessing here is actually an anti-gravitational effect where the local gravity created by this balloon overcomes the overall gravity of the Earth.
It doesn't overcome it. It's closer. And so.
No, actually, it overcomes it. It locally becomes stronger.
Oh, locally stronger.
Now, this is like, you know, you don't fall into the, I mean, I'm not falling into the balloon here or nothing like
It's
that.
not that strong.
But no, not that strong.
It's that strong.
Because the Earth field all around us being generated by every single atom in the Earth is huge. I mean, probably, I don't know, I would say millions and millions of volts equivalent. And you're not going to do millions and millions of volts on our balloon here, right? So what do you think of that? Could gravity just be the same thing as like this piece of paper stuck on my balloon? What do you think, Simon? Is that plausible?
Yeah.
I would think it's plausible. I mean, really, the only question that I have about this hypothesis is, you know, why didn't they come up with this sooner? You know, they've known about the electric Coulomb field for hundreds and hundreds of years, really, basically. And so why isn't the first thing that they looked at for what is gravity, you know, is, well, could it be the electrostatic force that we all know and love? Right? They should have looked at that. The first thing.
Well,
Instead,
there's a lot of people who get paid a lot of money.
and instead, you know, they're writing equations and talking about space-time and blah, 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 all those other weird theories I told you about, rather than go to the force that we know certainly exists on material objects. You know, logically, we measure the electric field on the Earth, we see it, we know it's there, and so to me, as far as plausibility goes, you know, it would seem to be very plausible that that gravity is just this electric force. And that's it. It's so simple, right? It's like, they should have come up with this 500 years ago. But no, to this day, people will vehemently deny that the electric field has anything to do with gravity. So I'm going to continue to try and convince you that the electric field...
They say that gravity has waves, but then they like find one in 100 years or something. So
Well, everything can have waves, really. Yes.
yeah.
But that's a different thing.
Oh,
So
okay.
I'm going to show you a couple other demonstrations here about electrostatic gravity. So
Okay.
I'm going to let's see here. I'm going to take my straw off the wall.
There's a straw on the wall.
The straw on the wall. See, probably you've seen balloons on the wall, but have you ever seen a straw on the wall? All I had to do is charge it up and stick it on the wall here. But, you know, I'm going to show how it really works to attract everything, right? So I'm going to charge up my comb, and, you know, and then I can just magically push it around.
Hey.
Right? Let's see if this works.
Hey, let's show your dad that, huh?
Let's see if this works. Okay,
Oh,
look, I
his
can
hand.
move it with just
His hand.
using my force of my hand.
Yeah.
Right? It's like I don't even need the charged comb to do it. Why? Because the straw is like, I mean, it was just used to be stuck on the wall. So it's charged, so it's attracted. This is what I say. This is an attraction of a charged object to a neutral object. I'm not charged, right? I'm neutral.
We
But
don't know.
we've got this attraction. And when
I mean,
this
we
is,
think you're not charged, but we don't know. Maybe
you can trust me.
maybe you speak the other way without charged.
I'm not sitting on a rug. So this is what I'm trying to show you, the attraction of a charged object to neutral object, right? And that's what I'm saying is gravity. Gravity is not, you know, people will say, okay, if gravity is just to charge, then the Earth must be positively charged. That means I must be negatively charged. I'm like, no, you do not have to be negatively charged. All you have to be is neutrally charged.
Oh.
Not negatives, not opposites.
Oh, right.
You have to rely on this dipole force, which is a bit different than
Yeah.
the direct positive and negative
I think he's
forces.
described by this combination of the black and the red. Yeah. Oh, the black and the red.
But let's try some other things. So people know that plastics are electrostatic, right? You know that. Let's try something different. How about wood?
We never think about that. No.
How about wood? Is it going to work with wood?
No.
Oh, it
Oh,
works
that's
with
right.
wood.
Oh, that's right.
It works with wood.
Because it's neutral. It's neutral. Oh,
Want to give that a try,
I
son?
see. So see, his hand was neutral,
Yeah, you have to get
It's
close, but not quite touching.
farther out, farther toward the end.
Yeah, try towards the end there. Or maybe this end. Or maybe it's not quite balanced well.
It's moved, it bounced.
Yeah, the wood is a little bit more difficult. Maybe I need to add a little bit more electricity. Okay. No, it only works for me. I only have enough charge.
Well, when you hand it off, does it?
See, maybe you should do it. You should rub your hair and use your hair. Yeah, just rub it up. And then put it at the very end, the tip. Huh. Still not working that great for you. Well, you know what? The straw is a lot easier. Let's do that. Okay. Now try. I'm sure that'll work. I think you grabbed it from the wrong side.
It just moved.
Yeah, grab it from that side. Okay.
Yeah, that.
There you go.
Yeah,
There you go.
grab it from the opposite end, yeah.
Let's see if you can use the force as well to move with just your hands.
Now he's saying hand, not comb.
Yeah, you just don't use anything, right?
See,
Except I got it so charged up that it
he's
must
saying
fly out.
you'll be
Okay.
neutral. You'll be neutral. There you
Yeah,
go.
there you go. That's a good party trick, right? Say, you have the force.
Yeah.
You can, that's right. See, pod 1, you have learned well. See, okay. Okay, now here's the controversial one. Okay, solid piece of steel. Okay.
Stainless steel.
Stainless steel.
The same as-
Piece of metal, right?
Mhm.
That gonna work? You know, that thing can carry charges.
Yeah.
That thing can. What's gonna happen?
Can it be magnetized? No.
Well, let's see here.
Oh.
Well, so far negative. Let's see here.
Not
Maybe just be
negative.
because I've not got it quite balanced. Come on, show me magic. There you go.
Oh.
There you go. There you go. We are doing it. We're attracting a solid piece of metal,
Yeah.
which I would say, the only reason why I'm showing you this is to show that electrostatics can attract everything, and they do everything, without exception, just like gravity.
That made me
Gravity
jump.
will attract everything. I mean, electrostatics will attract gravity, will attract everything just like gravity. You know, in fact, all the math for the electric force is the same as gravity. It's,
Oh.
you know, the only other reason people say that it couldn't be gravity is because it's so much weaker. Gravity, so much weaker than the electrostatic force. But I mean, that actually isn't a reason to say that it's different. It's just more dilute. Like if I have some red dye, and then I take a drop and I stick it in the bathtub, and I
Yeah.
see that red dye is 2,000 times less strong
Yeah.
than what's in the bottle.
Yeah.
Now, would we say that must be different? No,
Dilute.
it's just diluted.
Yeah.
And so that's what we have.
I still want to know what he's going to do with this.
That's what we have with gravity. Is just that gravity is a highly diluted form of the electrostatic force,
Yeah.
and it's also diluted because you're attracting a dipole,
Mhm.
which is the force derived only from the distance
Yeah.
between
Yeah.
the positive and negative poles,
So if it
which
turns,
is super weak.
so if it's turned sideways, it's not.
That's right. That would be an interesting prediction. See, this is an interesting prediction I would make, is that if you could see the dipoles in your body, that they would be pointing preferentially to the Earth. See, so I would think the negative ends of your molecules would be pointing downward, and the positive ends would always be pointing upwards. And if you flip yourself around, your molecules would rearrange themselves to keep pointing that way. Now, I've seen some evidence of this being true in MRI machines, and what they do is have a big magnets, and they go and they actually twist, they force, you know, this, they know about these dipoles, they force it to go in a certain way, and then they let it go, and then they return back to where they're supposed to go. And guess which way they're supposed to go? They go pointing toward the Earth. And depending on, you know, most MRIs are horizontal, but they do have some vertical MRIs. And it has some advantages because where everything returns is in a different orientation versus. So that to me, you know, I'm not sure about that, but that is certainly something from an experimental standpoint. I mean, this stuff can be proven. I'm just like, by saying gravity is electrostatic force, I haven't
Proven or demonstrated. Is that a proof? It's a demonstration. Is that a
I
proof?
don't know what the difference.
Oh.
The thing is that in science, you have to kind of like convince your peers
Mhm.
that your description is correct. And that is by a preponderance of the
Or
evidence.
better than
It's
any
very, very hard to actually
better than any other.
prove something,
Yeah.
right? It's
Yeah.
it's like, does it match the experiments? And so this is why I would suggest this as an experiment to prove
Mhm.
my hypothesis. So my hypothesis is just my idea, you know, not proven or anything. That's just my idea of how gravity is working. And certainly as part of that, and I think this is something we can do, And if anybody out there can do it, you should try this because you'll get the Nobel Prize if you can prove this.
Yeah.
That within a gravitational field, that the dipoles all align towards the gravitational potential. And you could possibly use this to try and defeat gravity. Like if everything was like pointed the wrong way, then the force of gravity would be lost. If you could just somehow, shake this so fast that it's pointing in the wrong direction, you could potentially release the grip of gravity, which is another thing that you could experiment with. And I have seen in my paper experiments where they have spinning ball compared to not spinning ball, and the one that's spinning does appear to defy gravity more. It goes higher. You see, then that would be a prediction that if you just try and scramble the orientations as fast as you can, that you can disrupt these dipole forces. So, and that's a good aspect of any theory, that you can make experiments and it can predict things that other theories do not.
Don't predict.
Right? For example, if the exploding Earth theory was correct, then spinning it shouldn't make any difference at all. But if spinning it does have an effect, then that would be in favor of, say, my theory. I predict that, right? Whereas, like, the whole Einstein space-time thing, it's completely moot on this, right? They don't say anything about
if you have
orientation.
a new theory of gravity, are you going to be the distinguished professor at some top university?
It could happen. That's what happened to Einstein. I mean, he was like nobody.
Oh yeah.
He was
That's true.
He was a rejected patent clerk who couldn't get a job in the university. And he was just doing this. He was just like me. He's just working at the patent office and spending his off hours thinking about
Then he changed
how this gravity works, and then he wrote 5 papers one year. And then 13 years, 21 years, it took a long time for him to actually get recognized. But he was a young man when he came up with those papers, and then by the time he was recognized, he was that old man we all know about, right?
And he got the Nobel Prize for the wrong thing.
That's right, he got the Nobel Prize for Brownian motion.
For light, for something about light instead of this gravity and...
Yeah, he got it for... Although people think that actually his wife came up with that one. And he just published that. You know what they call that? They call that the theory of relatives. That's my one Einstein joke. Okay. So getting on to what gravity... Okay, so I demonstrated that electricity, just like gravity, can attract everything. Yeah, we'll have to get to that when we start getting to what atoms are. But okay, so I'm sure you're dying to play with my biggest electrostatic toy here.
Yes.
This is called the DeGraff Generator. Some guy named DeGraff came up with this. Let's see here. Now, Ron, you don't have any pacemakers or sensitive electronics.
No.
Okay, but
I have lots of metal in my body, but nothing like that.
Okay, because this generates very strong electric forces, right? Which can take out all kinds of electrons. So I've unplugged everything here.
I mean, I'm wearing a watch. I have a phone in my pocket.
Yeah, so keep those there.
Not in my body.
What you don't want to do is take your watch and just like, stick it up there, okay? So keep, like, you're not wearing any electronics, right? So you're safe, right? Okay. So we're gonna go turn this thing on and just see what it does, first of all, okay? So all this does is just running a motor here with a big rubber band. And you think, well, how could that do anything? Yeah, let's see what happens. So turn it on. And suddenly we see our tissue paper just fly up. And so when you see that like that, that means this thing is charged and dangerous. Right? So how much charge? Well.
Oh my.
So there we go. We're creating a pretty big spark there.
Is that like a million volts or something?
Well, they say about 200,000.
Okay.
I think maybe I'm generating maybe 100 to 90,000.
Okay.
You want to try something? It's perfectly safe. You don't want to try?
Yeah. No.
Because I want you to feel there's actually a force when this happens. You can see the ball waving back and forth. You can actually significantly feel a force here.
Okay. Not much.
Curiously, it only happens when it actually sparks, and it seems to be a repelling force.
Yeah,
It
yeah,
seems like.
yeah, it repels slightly. Well,
But you can
for that
see.
matter, that thing moves. That thing moves.
Yeah, don't get your finger too close to that. Because
But it moves.
yeah, well, everything moves.
Yeah.
This is one of the things that forces, they work both ways. So it's like it's causing the top bell there to ring, and it's causing
Yeah.
the wand to also waver, right?
Oh.
So that's just an enormous source of electrostatic
Yeah.
energy here. So
Just by moving a rubber band.
I would say that what we've created here is actually, if my gravity theory is correct, a miniature Earth,
Hmm.
right?
Hmm.
That everything is actually going to be attracted to this thing, pretty much, right? Okay, now I might be cheating a little bit here, but I'm gonna demonstrate that with a few things here. So here we have a little bit of styrofoam
Styrofoam.
on a string here, right? And of course, gravity says you must fall this way, right? So if we turn on our mini Earth here, it's like, okay, it fell into the dome.
Mm-hmm.
And now it got charged, and now it wants to fly away from the dome. You have to start with neutrally charged. Yeah, whoops, see, that was just like the. See, that's a little bit weird. Normally it just sticks on there and then stays stuck. But maybe we've got.
But
So I
sometimes when you
So I have
demonstrate
to
it,
neutralize. I have to neutralize it by sticking it in my hand because I'm neutrally charged. So, because what's happening is that it's gaining the charge, and then it's immediately flying off. So I wanted to kind of, rather than stick. Although I can show that this is like totally anti-gravitational here.
Yeah.
You've got this little thing just flying around here. But there's even a more shocking demonstration that I'm trying to get it to do. Yeah, it keeps on. Maybe if I just turn this off here because it's overcharged.
Hey, did you turn this off?
Yeah, I turned everything off because I didn't want anything
Oh, I see.
on while I'm messing with the
Oh, okay. Your miniature Earth.
Yes, with my miniature Earth, and it sparks, and you can destroy your electronics rather quickly if one of those sparks
Oh,
one of
I
those
see.
sparks hits.
Oh. And you've taken the chance of having a child in the room with this?
Oh, sure. Let's see. A bigger child than me, but let's try this. I really want to capture this.
With gravity.
Now see, as soon as it gets close to the dome, it picks up the positive
Yeah.
charge,
Yeah.
and then it's immediately repelled.
Yeah. It's
But
caught on there a couple times.
But see, initially it did. Here, Ron, I need you to grab. I may have become too. But just grab hold of the. Just grab hold of the phone.
Oh.
I need to just.
Oh,
Yeah, there you go.
okay.
Discharge it. Maybe I've become too charged. Now it's supposed to stick.
That's right. Try me again.
Come on, let's do. It's like a magician who's trying to do the trick and it just doesn't work. He keeps on trying to do the trick. Although you got to admit the flying phone is pretty impressive, right?
The phone.
The flying
But
phone.
that doesn't seem like gravity, does it? That's
Yeah.
if we were doing that, we'd be flying off the Earth, right?
Yeah. It's the opposite of what you want to show.
Yeah, I want to show the. See, that's the attraction.
See, there you
That's.
go. That's the attraction.
I want to see the traction, but as soon as it
It
gets.
looks like there's a limit. You wanna,
Because you
close
have to
to
show the
close to not
neutral
touch.
attraction. As soon as it picks up an actual charge,
yeah.
then it repels. But getting closer, you can see it's attractive, right?
But how did the rotating rubber band cause this 200,000 volt?
See, this is once again the attraction. And if I were to do this right, I was going to demonstrate that this will actually be like this. That it will be.
Mhm.
I'll be holding it from underneath, and it'll be flying up.
Yeah.
But it's like, oh, it almost did it. Come on, do it. Do it. Why are you not doing it? You're doing it before.
This is.
Did you want to play with it, Simon?
No. No.
I'm afraid you get shot.
Oh, we know it's dangerous.
Yeah, it's kind of dangerous. Well, I'll give it one more shot here. Let's keep it there. There's the attraction. The attraction. Bring it close. It's not charged. No, but not
It is charged.
Maybe I need to, if I can kind of regulate the amount of charge that's on this by poking the pin into the field. You like if I poke the pin in the field, it goes down. First of all, let's turn this low. I'm gonna decrease the field a little bit.
Your life.
There you go. Touch that again. Touch the thumb. Just wrap it around your finger. There you go. I'm going to decrease the field. We're going to bring this. Oh, come on. Okay. There we go. So it's stuck. It's stuck. Okay.
Finally.
Let's get you
again.
stuck there.
Ah. So, what do we call on the pin? What do we pin?
Now we can't.
Let's see if
We
I can get this to actually work the way I want it to. How far can I go? All right. See, that's what I wanted to show you here.
Okay. Okay.
Look at that. It's floating upwards,
Yeah.
right, against the force of gravity. If you were that piece of stone bone, you'd swear you were standing on top of something. Because the force is going towards the dome,
Mm-hmm.
right? And I think it's quite far away.
It's still
That, okay. See, now it's working. See, now it's working good.
yeah. Huh. Okay. You don't know.
Here, Simon, you hold on.
It stopped working.
It stopped working.
Again.
Because Simon touched it.
I don't know, Simon, you're working all my experiments. But this is science. Sometimes things don't work out the way you expect them to.
Yeah.
But, yeah, you see? Look, Ma, no hand. No. But,
Just like when we're demonstrating software, we're trying to get a sale. We do our demonstration, it said, this worked yesterday.
Yeah, this worked
Why is
yesterday.
it not working now for you? When money's on the line.
okay, now I've just got some other random experiments. So if I poke the, so that tells me that there's no more charge. It's safe to touch. Okay.
What told you? The fact you touched it?
No, see,
Oh,
the
the
streamers
the
are
streamers.
going on. So here's
Streamers,
another, I would claim, anti-gravity. You've got the little balls in here, right?
Mm-hmm.
What do you think's going to happen if I turn it on?
They're gonna go
You
up.
think they're going to go up? Okay, we'll see what happens. Yeah, they're going up, they're going down, they're doing... Yeah, so what's happening here is that when the ball goes down, they get charged positively, so they get repelled, and then they hit the top cap, which is
Oh, I see.
leaking electricity out into the air. So that's a little bit negative. So then they come back down, and then they keep on going all over the place like they're popcorn.
Well, sometimes you stop in the middle. Sometimes you stick on the wall for a second.
Yeah, sometimes they
Have to
stick on
stop.
the walls for a second. But once again, I'm just trying to demonstrate the effect that electric fields can have on matter, right?
Still, I have to figure out how you get this from a rotating rubber band.
Well, the deal is with the rubber band is that you know how the comb and the hair,
Yeah,
that charges things up?
yeah.
Well, the rubber band and what we have in the bottom here
So,
is a Teflon roller.
a brush thing or something? Teflon roll.
Yeah, Teflon roller. And in the top dome here, we have a different material.
Yeah.
I think this is like a plexiglass or something.
Mm-hmm.
And what happens is that the rubber band going around the bottom roller, that's like you rubbing your hair against the comb. And what it's doing is that it's then taking those charges, and because this is a different material,
Uh-huh.
there's another comb here, and that's sucking those charges off. And
Oh.
it's actually, so this is actually an electron pump.
Yeah. Yeah.
And then it goes down and repeats the process. It's basically like an electron conveyor belt.
Conveyor belt. Yeah. Yeah.
Although this particular DeGraff generator is positive, so it's actually sending the electrons. It's actually sucking the electrons out of the dome and sending them to the ground.
Oh.
Is what it's really doing. But you know, for the purposes of figuring out,
I mean, this is the ground?
this is the ground.
Oh, this is.
This is the ground. This is why we have this banana plug stuck in the bottom here, so
Mhm.
that it will complete the circuit. That's why we get the big sparks, because it's sending all electrons down here and sucking them all out of here. So when we stick the wand close, they all want to jump back to the dome.
Mhm.
And there's actually another device here, which is what I was using to poke the electrostatic field with to kill it.
Mhm.
It's very subtle that this is sensitive to either positive charge or negative charge. And it'd be extremely hard to see, but when I stick this on the top of the dome, the top of it lights up very brightly, showing that it's detecting a positive field. Whereas when I stick it down in the bottom here, you'll still see it flash, but it's actually flashing from the underside.
Oh.
And that indicates a negative charge. So
Oh, I see.
let's see whether you can see that. Okay. So if I put this close,
Oh, yeah, it is.
you can see that it's
Yeah, there's a light.
it's lighting up there orange.
Exciting to see it.
You know, if I take it away,
Yeah.
nothing.
Yeah.
Put it close, we see the light.
Yeah.
But now you can also get that to happen when I stick it down here.
Oh, but it's a different flash.
But it's actually the bottom that's flashing, not the top.
Yeah.
So we go here, we get the top and the bottom. It starts flashing at the bottom. So I'm not sure how they did that, but that's an interesting little trick.
Mhm. Good, good.
Use that to discharge things. So there's another little fun little thing. This is a pinwheel.
Simon, you can impress your friends and say you saw a DeGraff generator.
This is a little pin. We're gonna stick it on top of here. Balanced perfectly. So what's gonna happen here is that the electricity is actually gonna fly off because it's attracted to anything that's pointy. It's gonna fly off the points.
Oh.
And let's see what happens. Come on. Okay, so it's should spin. Come on, guys, spin. Okay, there we go.
There you go. There you are. Huh, because it's coming off the end.
Yeah, it's coming out the ends.
Yeah.
This is like a form of propulsion.
Yeah.
They actually make things called lifters, which, based on this, can actually lift off the ground because they're pushing this small stream of ionized air out.
Is there an application you use it for?
Well, it's spectacularly weak force. You know, you can get small things to levitate with it, but
I think so. It's not.
But Elon Musk can probably not use it. Although I would tell Elon that if he wants to launch his rockets, and if gravity is just the electric force, and that the Earth is just a positively charged ball, well, how do you make the electric fields repel? You
Yeah.
just but you charge your if you just charge your spaceship up to a very high positive
Oh,
charge,
yeah.
it would
Oh,
repel against the charge of the Earth.
you never thought of that. You better tell him.
Yeah, I said, yeah, Elon, if you want to lose, you know, maybe a % or two off of your liftoff weight, give that a shot. You know, even if gravity isn't electrostatic, we know that the electrostatic force is there.
Yeah.
So all you have to do is just leverage that,
Mhm.
make your ship opposite to whatever it is locally,
Oh.
and yeah, that will for sure
Mhm.
lighten your load, right? Even if gravity isn't electrostatic. I mean,
Mhm.
just based on what we know, that should work.
Mhm.
That's what I figured out.
What did you figure out?
That basically, when you're on an elevator, it seems like it's going slow, but it's really going super, super fast because you want it to get higher than how high it is at that second.
Yeah, it's amazing how fast elevators
You
go
talking about how
up.
fast it goes or how it feels?
Because initially, when you're in the elevator, all you feel is for a little while, and then
And then you don't
they
feel
don't
it.
feel anything.
Yeah.
And then it goes, woo, and you get a little lightheaded.
Yeah.
That's what.
Mhm.
And those are the accelerating forces. Like I said,
Yeah,
with the
but in the middle, you can't tell how fast you're going. Yeah.
if you are subscribing to the exploding Earth theory, then you would think that we're all just experiencing the initial rush of the elevator, right? And I'm not exactly sure what the purpose of this demonstration is, but since I've got it, there we go. It levitates, right?
Yep.
Although that's not nearly as impressive as levitating like little piece of foam and stuff like that.
That you're holding in your hand.
That's,
Yes.
that's the impressive part.
Mhm.
So what do you think of that site? Pretty cool, huh?
Yeah.
Pretty cool. So all you have to do is prove that that is in fact gravity, and then they will give you the Nobel Prize. That's it. Easy. Right?
Impress your friends.
Press your friend. Just say, you know what, I know what gravity is. Ha, you don't. Oh, wait a minute. I do have one final demonstration. And I'm going to use my froggy for it. Okay.
Oh.
And this is going to make a little bit of a mess. Okay. Hopefully not too much of a mess. So, we're going to put my bubble solution in here. There we go. We're going to stick them on top. Mr. DeGraff Generator. There we go. Careful.
He's kind
Okay, so this is one of my favorite toys from Dollar Tree. So if we turn it on, it makes bubbles.
of.
And you'll notice the bubbles, they're reacting to gravity. They're just falling straight down, right? All right. So what do you think going to happen when I turn on the DeGraff Generator? You think they're going to fall faster? Or you think they're going to fall up?
Toward the
Are they going to, what are they going to do?
toward the center. That's my guess.
You think
Based on what?
it'll go towards the center? Okay. Well, it'll do something, and I'm not exactly sure why it's going to do what you're about to see. But let's just see what happens. Although my prediction is that if the Earth is a positively charged ball and this thing is generating positive charges, that's going to make those bubbles positively charged. Therefore, like I was suggesting to Musk, that that will make the bubbles lighter.
Go up.
I'm predicting that they're going to go up.
Oh, okay. Yeah.
Right? Okay, but we'll see what happens. So we're going to start off, DeGraff Generator off and generating bubbles. Okay, they're going down. Turn it on. Now I have to reduce the strength here a little bit. So what do we have? We have bubbles going everywhere, including some going straight up.
They are going higher.
There are a few that are going way higher. Way out. They're going way over the place. They're attacking the bubbles, right? Okay.
And it's attack, and the bubbles are attacking
But this is
me.
what the bubbles normally do. It's not very exciting. Okay. But, I find it interesting that, we know that the bubbles are all kind of running away from each other because they're all kind of positively charged, and some of them are going down.
They still went down, but they did go higher.
But certainly a lot of them went a lot further out,
Yeah.
and some of them went up,
Yeah.
as if they were filled with helium.
No, it wasn't a matter of healing. Well, that's playing with gravity too.
Now, see, because you know that with regular gravity, they all go straight down. None of them got here. None of them.
Mm-hmm.
But when we did this, it's like, well, maybe they got all pushed apart each other very fast. But, I was pointing out to the bubble that was just staying there in complete defiance of gravity. Because, they're not all, floating away. I mean, I would have predicted they would all go straight to the ceiling. But no, they didn't exactly do that. But
Two kinds of gravity.
But certainly, they did something, I would say, at least unexpected. So.
Mm-hmm.
Do you know what my question is?
What is your question?
Why there's white and black on that?
Oh, we'll get to that when we get to, I don't know, what is light?
Mm-hmm.
All right, what is light? All right, so I have one. So that's the DeGraff Generator, but I have one other little toy here. It's fun. It's called the fun.
We want to go for about another 20 minutes.
You can only go for another 20 minutes.
Yeah.
Okay,
But you might give us a reason to want to come back. You see.
Okay, let's see here. So here's another thing here. Did we get this to work? There we go.
Oh, look at that. Look at that.
This is another demonstration of anti-gravity. Okay. What's it called? This the fly stick.
Fly stick.
I'm gonna try that. You have to press the button. Press it. Keep the button pressed all the time. Keep it pressed. You shake it off. And you have to get under it.
Underneath it.
Wait a second.
Hey, there you go.
It's going all over the place.
That's right.
Pretty good.
But that's fun. That's, once again, people would normally say, oh, that's just a little novelty. Doesn't have anything to do with gravity.
Why is this part important?
Well, actually, this is if you looked inside of it, it's exactly the same thing as this. Small DeGraff generator in here.
Wow.
There's a small rubber band. When you press this, the motor is running small rubber band.
Yeah.
So it's generating high electrostatic force, which we can then use to defy gravity with. Right? So I'm saying that gravity is just the electric force. of course, then you probably got, well, what's electric force, right? You're not telling me anything, right? It's like, why should any positive particle be spontaneously attracted to any negative particle, right? Well, how does that happen? This is one of the greatest science mysteries.
Oh,
I mean, that too would seem to take energy.
I thought
Right.
Einstein
Do
figured
that.
everything out. No?
No, he didn't figure nothing out.
Oh.
So we have gravity. Gravity is, I said, just electrostatic force. But then we still have the question of, why do positive attract negative? And this is a very, very difficult question. And so, it's like some people think that, well, the electron is sucking down something and the proton is spitting out something, so that's what makes them attract, except why do two electrons repel them? Because they're both sucking, they should be attracted to each other. Those kinds of explanations don't work. There cannot be something that has a direction to it, because then, that would cause two electrons to be attracted, or two protons to be attracted to each other. The math doesn't work out. So I came up with a way of trying to figuring out what that is.
Mm-hmm.
And that has to do with the fact that whenever you see anything move, it's usually just a push, right? So if you see that, and it goes that way, because, something hit it, right? Because, so whenever you see something being attracted to each other, I mean, actually, it's two things. Like if you have billiard balls on a billiard table, the only reason why two balls would ever approach each other is if you hit one ball towards the other, always from the outside of the two. So whenever you see anything attracting, that's actually something from the outside coming and hitting it from the outside.
You with a stick.
And similarly, if you have something, you see two things coming apart, there actually has to be something in between them, hitting them apart, right? It's always a collision. There's only collision forces are allowed in Newtonian physics. So what I found is that, and this is not my idea, and that is that I think the electron is like this pot. And when you hit the pot, it rings. Doesn't matter how hard you hit it, doesn't matter how many times you hit it, it rings at the same resonant frequency.
Same frequency.
Same frequency, no matter what.
See, Simon, the frequency is how high the sound is.
Right?
Higher
No
frequency is
matter
higher
how
sound.
hard you hit this, you get the same sound.
You get the same sound.
Right?
Yeah.
So that's what I think the electrons are doing. They're out there, they're banging into each other, just like these two blocks are. You can hear the sound it's making. Right? Now the thing is that this is ringing at a specific frequency and a specific phase. I could represent that by, like this. This is a wave, and it has a specific frequency, and starting right here, it has a phase. Like it's higher at this point in time and lower at this point. Now, if I had another pot, but I reversed the phases, so it goes down and then up, down and up. Now what would happen is that these waves would cancel.
Would cancel out.
Which means that you're left with flat lines. This is how your noise canceling headphones work. So therefore there'd be no energy between them. Now I have my two pots.
I don't know about the no energy. Energy's canceled
Well,
out.
the thing is that the energy from the pots would be canceled out. So if I have my two pots,
So that means
and they're ringing, and the waves are canceling in between, but there's still waves on the outside.
Yeah.
I'm saying that it's higher energy outside the pots,
Right.
and that is causing the pots, that will push the pots together.
Oh.
Because there's not as much force between the pots,
I see.
but there's more forces outside the
I
pots.
see.
So this is the key for, what is a positive charge, what is a negative charge. That the only difference is that the pot is somehow ringing always 180 degrees out of phase
Oh, I see.
with the other pot.
Mm.
And that may be a little bit of a stretch.
90 degrees. out of
90
phase.
degrees, they're always out of phase, and they always have to be out of phase. That's the only way this works.
Mhm.
That they have to be exactly the same frequency, and they have to be exactly out of phase.
Yeah.
So if you have all those ifs,
And they're the same strength.
and if they're the same strength,
Yeah.
well, even if they're not the same strength, they'll still cancel. It's just that we'll leave some residual
Leave some-
other
Yeah.
way.
Yeah.
But this is the way I think about it. Is that the only reason why the negative and the positive in electrostatic force are attracted to each other is because they're both ringing like my pots.
Yeah.
They're ringing same frequency, out of phase, and so that when they are out of phase, they're being pushed together like that. But the opposite happens if the same phase. If they're the same phase, then
Yeah.
all the waves they add up.
Yeah.
So there is bigger wave between them.
Yeah.
So that means there's more energy between them. This pushes apart, and you get the beautiful result that it doesn't matter whether it's negative or whether it's positive. Both of them will push apart.
Mhm.
Only when you've got opposites will you get the cancellation and the attraction. So in that way, this is the beautiful explanation for how positive and negatives actually work.
Yeah.
Because ultimately is that the electrons are exactly the same as the positive. Now the opposite of electron is actually a positron, right? Not a proton. Proton is much bigger than a positron. So positron is the antimatter partner of the electron.
Mhm.
But in my theory, actually everything in the world is made of just positrons, electrons. That's it. And actually, the positron, electron, they're the same thing. Physically, they're both. All they do is they ring like my
They ring.
pop.
They ring.
That's it. It's physically exactly the same thing. The only difference is that they ring at an opposite phase.
Okay, since we're going to finish up in about 10 minutes. I want to see what that does. Do you want to see that more, or about the black and the white?
Well,
Well, now the only reason why I have this here, okay, I'm scooting the lid here, is because it's cool, but it also explains what matter actually is in a tangible way. That you can see that matter can do stuff.
and guess what?
What you're seeing here are actually electrons.
Oh,
So you see them? Okay, well actually you're seeing the light being generated by electrons.
well,
But I assure you, they are there. And it's as material as this cone. Right? Inside this cone,
how far do the electrons move?
well, they're moving all the way from the center of the dome, obviously, to where you put your finger.
Okay,
You can create a very bright streamer of those electrons there.
by focusing.
Because they are coming off of that ball, coming to my finger, going through me, electrostatically shocking me, but it's a good demonstration to show that I would say that electrons are real. They're a real thing, you can really see them.
Mhm.
And I would say that they're as real as this
Oh,
cone.
But you said we're not seeing them, we're seeing the light they generate.
Yeah, that's because they're so very small. But it exactly traces the path of where they are. Yeah. Now, for some people, see, we don't actually know what an electron is, actually. And even I don't even have any idea what an electron is, actually. So if anybody has any really good idea of how is it we can have some particle which, like my pot, rings, that would be great. But otherwise, no.
All the smart people are studying it, we don't,
All we know is that electron is the most fundamental particle. We can't break it up into anything. We've never seen it broken up into anything, so it's fundamental, along with the positron.
How about a Higgs boson? Is that,
Well, you know what the Higgs boson is? Now, the Higgs field is a thing that gives everything mass. Now,
mass?
this gets to the question of what is space made out of. Right? Now, they said that the Higgs boson, now the Higgs boson idea is not bad. The idea is that space is filled with something, and when you put a particle through it, they have to move aside, thus taking energy, thus giving things mass. except that the thing that they've decided it was the Higgs boson, lasts about a trillion billionth of a second.
Yeah.
How could that be the thing that's filling space if it only lasts a trillionth of billionth of a second?
Yeah.
No, that doesn't make any sense. So this is what I said. So I love positrons and electrons. I say they're the most beautiful thing ever. Okay? And so what I'm going to do is I'm going to fill all of space with positron electrons. See that this positron electron, they love each other. Although science would say that when a positron and electron get together, they annihilate, they disappear. But I say no, that is wrong. When a positron and electron get together, they form what is basically a neutron. They come together, bang, we hear it releases energy, which we see as gamma rays, but it leaves behind a very hard to detect neutral particle. So that would be the biggest lie ever, which is, and this is one of the mysteries of science, which is like, how does annihilation happen? Where did the matter go?
Well, and also, this has to do, how does light propagate through space?
How does light propagate through space?
Something.
See, currently, science does not recognize the existence of what has been called the luminiferous ether, which is a medium. Because if light is a wave,
light's a wave.
The first question is, what is it waving through?
Yeah.
So what I'd say is that space is just jam-packed of these positron electron dipoles. I've given it the new name, the posilectron. But it's essentially, I think, the same thing as neutron.
Did you touch that? Yeah.
So you fill all of space.
Do you want to? No?
It's fun. It's perfectly simple. So that answers the mystery of, what is light? It's actually strictly a compression wave, just like sound. Exactly like sound, and nothing any more complicated than that. So our little dipoles here are just the medium for that. Now the other thing is that it also serves to produce the Higgs field, because you just need some matter, that's something's there that it interferes with the motion of
now, I'm not trying to find a stopping point here. Simon, is there one more thing that you want to see demonstrated on this table?
This.
Okay, what we have here, this is called the Geiger counter. And what this is doing is demonstrating the actual a demonstration of particles from, say, outer space, little particles, hitting it and actually registering.
Oh.
And I have to be very quiet, you can listen for the click. Click. Where's the click? There's 2 clicks.
Yeah, I heard too. Doesn't need
So this is kind of showing like very much, not really wave kind of thing. Although the gamma rays are actually waves, but they're in tiny little packets.
Yeah, Simon, these gamma rays go right through us.
Because some people think that light is a wave or light is photons, light is particles, waves. They're both. It's very confusing. Now I would say that light's strictly a wave, but we have wave packets like gamma rays, just packets, right? It has a beginning, it has an end. Like the gamma ray could just be like this. That's it, done. And it travels through space as a fixed packet. It has fixed volume. So for all intents and purposes, it may look like a particle, but it's not.
Now we're surviving with gamma rays coming all the time, so they're not dangerous, are they? Are they dangerous?
Gamma rays, yeah, gamma rays can penetrate you quite deeply. Now, and one of the interesting things about this detector is that it comes with its own radioactive source. So gamma rays are kind of dangerous, but beta rays are actually electrons being shot out. So we have the radioactive substance right there, right? So it took a long time to hear clicks with that, but if I put this here,
Yeah. Oh, because it's in
See,
there.
then it's going crazy.
Yeah.
So every single time you hear it click there, that's an actual electron
Yeah.
hitting the Geiger counter detector.
Detector. Yeah.
Right? So I just wanted to impress upon you that electrons are particles. They're not clouds, they're not waves. They are, I mean, the mainstream scientists say, don't think of electrons as hard little balls. Says, no, I would exactly say the opposite, which is an electron totally is a hard little ball.
Yeah. Yeah. Okay.
Right?
Yeah. Okay. I think this is a good time to finish up.
And what's
Let's see here.
this
What?
part about?
Well, here, you got to do the magnet demonstration here. Okay.
Oh, okay.
We've got
Okay.
we've got my old vintage TV here. Okay. Here we go. All right, so I've got my old vintage VCR here,
Camera there.
and we're seeing the cross here. Now, I don't see. We're talking about magnets and how magnets work. Magnets are very mysterious things.
So that cross is that cross there?
That cross is that cross. See, if I put my fingers in that, you can see.
Oh,
Fingers are there.
okay. Okay.
It's a live picture. So, but the way magnets work is that they bend electrons. They force them off course. So what I have here is gigantic magnet.
It's not the way they work, it's the effect they have.
Yes, the effect it has. So I've arranged this here so you can see how the magnet bends the electrons. Because normally these are all going to come straight out into the screen here. Make a nice cross,
Yeah.
right?
Yeah.
Okay, but look what happens when I stick the magnet close to it.
Oh.
You can see it twisting.
Oh, it's twisting.
It's twisting.
Hey,
If I do it the
Right.
opposite way, they twist in the
Twist the
opposite
other way.
direction. Right?
You like
I don't
the
know if the
rainbow
camera can
effect?
see that, but okay. So we go, we do this. It's twisting it.
yeah.
It's almost like there's like some kind of circular vortex.
Oh, why did you twist the TV set?
Hmm?
Why did you twist the TV set? Did you twist
So
the
that I
TV?
can, so that the camera can see.
Oh, I see. Okay.
Otherwise, it's really hard to see.
Okay, okay.
But
Yeah,
this
yeah.
this is the action that
Yeah.
a magnet takes. That
Yeah,
it takes something and it
and that's a strong one.
it deflects it, right? So if I have an electron here and I have a magnetic field, what it's going to do is it's going to go and cause it to go that way, see? Now the question is, what are you feeling when you have two magnets coming together? What is going on? Now I would say, this is controversial, that when you have permanent magnets like this, that there must be a current loop in it. Because this is the only thing that we know actually creates magnetic fields. So I would say that there must be a superconducting current loop in this permanent magnet somewhere. Right? People are all jazzed up about room temperature superconductors, but I would say they're already here.
Oh, I see.
They're in this magnet. They are looping around in this magnet. Now the thing is that when you bring another magnet close to those of the electrons in here, it's going to cause the same deflection that you saw on this screen.
Oh, I see.
So the magnet, it's happily going around in this magnet. And when I bring this magnet to it, it's going to cause it to deflect. It's going to cause it to deflect towards the other magnet. But guess what? This is stuck. This is stuck inside this other magnet. So when this deflects, it's going to drag the rest of this magnet with it because it can't escape the magnet. If it was free, the electron would fly out of the magnet.
Oh.
But it's not.
Stays in there?
It's stuck inside the magnet. Magnets are made out of like ceramic magnets. You know, why is a magnet made out of ceramic? It's non-conducting.
Oh.
Why are they made out of this material? Why not just solid steel? Because in solid steel, the electrons could migrate
Oh, I see.
and
Couldn't
fly out.
Yeah, I see.
But if they're trapped like this,
I see.
then, I have a video, and it's like you have two bird cages, and you put feed in between them, and all the birds try and fly towards the feed. They're going to drag the cages towards the feed. They're going to drag.
Oh,
So what you're feeling here is that you have the electrons basically flying towards the other magnet.
Mhm.
And so you're just feeling the electrons flying towards each other at opposite sides. And that's how you get the magnetic field.
You're getting pretty theoretical for us now. I think it's time to finish up.
But let's see here.
Yeah.
We've got that, and looks like we've shown you that.
Well, there's more for us to see next time.
Yeah, we can play with what you can do atomic theory. So
Yeah.
how atoms
Okay.
are made.
Okay, there will be some things to see next time, right?
Oh sure.
Okay.
We can play with Legos next time.
He does that at
You
home.
see, we got and
He does
this,
that at
this gigantic thing here. Right?
Yeah.
Haven't gotten close to explaining that.
Yeah, okay, thank you.
So next time we can play with Legos.
No, he's got so many Legos at home, you can't believe it.
All right. Well then, thank you,
Yeah,
Ron.
yeah, thank you very much, yeah.